Welcome, folks, to this talk on predicting anomalies before they can result in critical failures. An expert car mechanic, by just listening to sound of your car motor, tell you if your car is going to break down in coming weeks or a month. We are trying to do something similar over here, except we are going to use AWS IoT and Amazon machine learning services to give us that insight, which can point to the anomalies, which can predict the things that the car mechanic was trying to predict. I'm Atul Bargaze. I'm principal IoT consultant here at AWS, and I'm joined by Yushin Yang today, who is one of my colleagues for this talk. So this talk is about our journey with one of Amazon's internal team where we implemented failure prevention. So we are going to talk to you about how we went about implementing failure preventions at one of the facilities, which you can see here in the picture. We deployed a plethora of sensors, some of which are shown on the right-hand side corner of the screen. We are going to focus on two sets of sensors among the sensors we deployed at the Amazon facility: air quality sensors and vibration sensors. So we're going to take the data captured from these sensors and we are going to show you how we implemented predicting anomalies which can point to eventual failures. So let's get started. Here's the agenda for today. We'll start off by talking about where and how to start gathering the data that you will need in order to predict the anomalies. We will then talk about how do we process the data which we captured in order to make it suitable for predicting anomalies. We will discuss various approaches for predicting anomalies. Yushin then will dive deep into some of these approaches. And towards the end of our talk, Yushin will conclude with a quick demo of the process by which you can predict anomalies which can point to eventual failures. So your predictions are going to be as good or as bad, you can say, as your data is. Your data is going to be critical for predicting anomalies. So let's talk about where and how to get this data in order to predict anomalies. Some of the good sources of data can be critical equipment in your facilities, in the factories or in oil fields that you want to monitor for abnormalities. To give an example, if in an oil refinery, if you have a rotary pump which is connected to a pipe which forms a critical equipment, start with identifying the rotary pump and then talk to the stakeholders associated with that equipment. Talk to site managers and maintenance persons responsible for these equipments. Add instrumentation to these critical equipments to start gathering data. Once you have identified the critical equipment and potential failure points, the next step is start gathering data by adding sensors. And some of the very commonly used sensors in industry are vibration sensors, which can give you information about vibration readings from your industrial equipment. Electric current consumption can be obtained by tapping into motors, electric current consumption, which can point to important sources of anomalies. Ultrasonic flow meters can be deployed to capture flow of liquids through pipes. Temperature and sound sensors are very cost-effective way of adding instrumentations to your equipment in order to gather data that you are looking for. So these are some of the ways some of the sensors you can add to your equipment to capture data. Now let's look at how to start capturing this data. Any sizable IoT deployment, capturing data from multiple sensors, hundreds, thousands, or even millions of sensors, can be a challenge in itself. And this is where AWS IoT can help you do a lot of heavy lifting. So let's look at how you can start capturing data using AWS IoT and let AWS IoT do the most of the heavy lifting. When you're dealing with mobile equipment, such as vehicles, farm equipments, cars, trucks, these mobile equipments, they have sensors attached to a telematic unit. Now, this telematic unit would be sending the data over some cellular network through 3G, narrowband IoT, or even 5G these days to AWS IoT. If you're dealing with warehouses where you would come across forklifts, pallets, and other packaged equipments which can have sensors deployed on them, these warehouses, they will generally have some sort of a local network. LoRaWAN tends to be a very popular network technology used these days. And you would have some sort of a gateway. In case of LoRaWAN, there will be a LoRaWAN gateway which would do the protocol conversion and send data to AWS IoT. In case of factories, you will have programmable logic controllers. These programmable logic controllers, or PLCs, would be sending data to OPC UA servers. Now, you'll need some gateway to do protocol conversion. AWS IoT Greengrass with Sitewise can be that gateway to do the protocol conversion from OPC UA and send data to AWS IoT to capture your data. Now, similar to factories, you could also, in case of buildings, there will be sensors deployed all over, sending data to a building controller. You will again need a gateway to do the protocol conversion from building controller to send data to AWS IoT. So these are some of the ways you can capture data. By no means an exhaustive list, but some of the important patterns for capturing data. Now let's look at how do we process the data that we have captured. So some of the strategies for processing data, you can start by processing data at the edge, close to the sensor. There are pros and cons associated with processing data at the edge. The advantage is you can save on bandwidth cost, you can do some processing close to the source. On the flip side, you will need compute unit on the edge, which can increase the cost. You will also incur the headache of managing the deployments, edge deployments. Another strategy for processing data is process data in batches. So you would aggregate a set of events in a time window and then process a batch of these events in one batch. If you need immediate action in response to the events, you would want to use some sort of event-driven architecture to process the messages coming from your sensors. You could also combine the batch processing and event-driven architecture into some sort of a Lambda architecture. And that is something commonly used these days in industry, where you have combined event-driven and batch processing architecture. When you're dealing with data coming from sensors, most often than not, this data will be a time series data. And time series data is basically a sequence of data points indexed in time order. Most often, these these data points are equidistant to each other, but in some cases they may not be. Now, time series can be a univariate time series where you have one variable being captured at an instance in time, or you could capture multiple variables for an instance of time. For example, you could capture temperature, pressure, vibration for an time instance, which makes it a multivariate time series. Now, let's look at how you would process the time series data to make it suitable for predicting anomalies. In most sizable IoT deployments, you will have sensors that are generating data at different frequencies. For example, sensors deployed in industries, factories, PLCs attached to these sensors would be capturing data at millisecond interval. Current readings would be captured by your current sensors every second. And temperature and humidity readings, which don't change very often, can be captured every minute. Now, what we want to derive is a time series record, which looks something like this, where you have a timestamp and a set of readings associated with time with that timestamp. We need to derive this time series record from sensor readings that are reporting their readings at a varying frequency. Let's look at how we can do how we can accomplish this. Now, for sensors which are reporting every millisecond, what you want to do is you want to aggregate these readings. Now, this is an excellent candidate for aggregation at the edge. However, there is a caveat associated with this. You want to choose an aggregation interval that doesn't miss on important signals. For example, if your anomaly happens to be within 1 second and you're aggregating in 1 second, you might completely lose away your aggregation, your anomaly by your aggregation process. So aggregation interval is something to be arrived at by carefully looking at your data. Now, the data coming from your sensors, which are reporting every second, you still want to aggregate them in the cloud and window them because every sensor probably would be reporting the readings at different instances. And what you want is reading for a fixed time instance, which can be correlated with other readings. Sensors reporting at a slower pace every minute, you want to fill in these values. So you'll be duplicating a lot of data, but in order to come up with a time series record like this, you'll have to fill up those values. So having looked at time series processing, let's look at the architecture that is commonly employed for processing the time series record. Here is a very common architecture where data is being ingested. And what we are doing is we are processing the data using real-time processing pipeline and a batch processing pipeline on the right-hand side over here. Yushin is going to go into details of this architecture later on. Let's look at some of the approaches for predicting anomalies. Now we have the data that is needed to predict anomalies. Now, the approaches for predicting anomalies will depend a lot on the data you have. If you have unsupervised time series data, the time series data we looked at, what you can do is you can detect anomalies. And detecting anomalies could look something like this, where you have a blue waveform generating your sensor readings, and the anomaly readings are shown on the red waveform. The anomaly detection can be done using statistical method or machine learning. Some of the common machine learning techniques are random cut forest and k-mean square. If you have supervised time series data, you can do forecasting. And what I mean by forecasting is if you have labeled data where a domain expert can associate failure condition with your data. You can capture these annotations, and you can generate a supervised time series data, which can help you do forecasting. Forecasting has been done traditionally using statistical methods, but increasingly machine learning techniques like ARIMA, LSTM models can be used to do forecasting. Or you could use Amazon Forecast, a fully managed forecasting service. If you have image data, you can do computer vision, machine learning. But we are not going to dive deep into CVML today for sake of time. So that is a good segue into our next section, where Yushin is going to take you through deep dive on some of the techniques for predicting anomalies.
So before devices fail, they tend to show different anomaly behaviors. They could go like this. They could go up and down, sudden jumps or surge or dive. Or they can show this kind of a skipping a heartbeat kind of pattern. This happens a lot for rotary pumps, where the vibration magnitude tend to increase before they fail. And this happens a lot for weight or temperature or humidity, and they tend to drift from their originally calibrated parameters. And for rotatory pumps, again, they could increase their vibration amplitude, vibration frequency and amplitude before they fail. And finally, we also can see this kind of anomaly pattern buried underneath. So we might not have visual clue that anomaly is happening, but with accurate enough models, we should be able to detect those kind of anomalies. And we ranked these anomalies from easy to detect to more difficult to detect. And in this presentation, we're going to show you a two-step strategy of detecting those anomalies, it's a trade-off between complexity and the latency that you can bear with the inference. Now, step one, let's predict failure through immediate anomaly detection. As Atul mentioned, for this Amazon Fulfillment Center project, we're detecting temperature and humidity and other gas pollutant. And we want to set a strict threshold, and whenever they go beyond those threshold or sudden jump or dive, we want to notify the site manager as quickly as possible so we can ensure employees' health. And for this use case, we want minimum latency, and we implemented on AWSkinesis Analytics application. Now, within Kinesis, there's this built-in algorithm called random cut forest. And this algorithm is a very practical algorithm for you to compute your anomaly score on every single observation that comes to you in your data stream. And in order for this algorithm to work, you first partition input space into random samples. And for each random sample, you randomly cut through any random feature. And points alone would become tree leaves. And you compute anomaly score as inversely proportional to the tree leaf depth. Intuitively, you can understand this as the harder it seems to isolate one data point from the rest, the more normal that data is, and vice versa. And this algorithm is a built-in algorithm for Kinesis Analytics. So you can just run this one simple SQL command, and then this algorithm can be implemented. Now, to show the simplicity of this algorithm, we came up with this two-dimensional data set. And on one dimension, we have a data series vibrating at lower amplitude, in this case from -1 to 1, and then the other is from -10 to 10. And interestingly, the orange line is the anomaly score computed for the two-dimension data set altogether. And we can see that for that small bump on the smaller amplitude dataset, we can see a sharp rise in our anomaly score, meaning that it is able to detect anomaly on that smaller amplitude dataset. And this gives us two benefits of, this shows two benefits of implementing random cut forest. First, you can compute on any multi-dimensional dataset. You do not need any kind of normalization for you to compute the anomaly score. Now, there is a challenge for this kind of random cut forest algorithm. So in this case, for example, you see we have a sine wave vibrating again from -10 to 10, but every once in a while it becomes stagnant. You can see that flat line showing that it is stagnant. It can either be caused by sensor failures or it can be caused by just equipment shutting down. And counterintuitively, we can see the anomaly score in the orange actually drops instead of rises. And so this becomes counterintuitive for us to understand because naturally we want to have a higher anomaly score when we actually detect a higher anomaly. So in this case, we have a solution for this. Instead of using anomaly score as a raw data and setting threshold on top of that, we take the delta of it. We take the first order derivative of it, and then we compute absolute value of the delta of anomaly score. So in this case, although the anomaly score actually dropped, but then the delta, the absolute value of the delta actually increased. And this algorithm is also very easy to implement in Kinesis Analytics by only these few lines on your data stream. And as a result, in the green line, you can see the absolute value of the delta of anomaly score. And together with the dip of the orange line, which is the actual anomaly score, you can set a threshold on the absolute value of the delta of the anomaly score to detect and send alert to your site manager if any anomaly is detected. Now, another challenge for random cut forest is it's actually not very good at detecting trending data. In this case, we have a sine wave, but a slight bias introduced in this sine wave. As you can see, the blue line is trending up, but the orange line showing anomaly score and doesn't change much is still varying in the same range, and there's no clue to tell that the data is actually trending. And a solution for this would, again, be in data analytics pipeline, Kinesis Analytics. And this algorithm is called sliding window. So for each single observation, we look back for several observations happened before, and then we can either take average or run some other computation on top of that window. And in this case, by implementing sliding window, we have a line trending up, and we can further implement some kind of threshold or aggregate differently as a tool mentioned, and we can send alert with this type of algorithm. Now, so far we have successfully covered the simple cases of anomaly detection. How about this? How about if we have a sine wave, but you can see that this blue line is actually a sine wave, but with every once in a while, the phase of this sine wave shifts a little bit. And with this kind of out of phase periodic measurement, as we can see that anomaly score does not perform very well, and there is no indication that the phase has shifted. And it seems like this is a challenging scenario that Kinesis Analytics cannot solve for us. That is exactly why, oops. That is exactly why that we, So far, we have covered those 4 types of anomaly score on the simpler end, but for the remaining 2, we have not yet found a solution to detect this type of anomaly. And That's why we implemented step 2, prediction of failure through pre-trained models. So in this case, as we remember correctly before, in step 3, we have a Kinesis data analytics pipeline as our first step. And then the second step, we leveraged another service, AWS service called Sagemaker. And for those of you who are not familiar with Sagemaker, it is a fully managed ML service that helps you to train and deploy your model easily. You can easily launch a notebook instance, and you will have all of the popular frameworks such as TensorFlow or PyTorch or Caffe already implemented for you, and you can directly use these frameworks to start training right away. And once you're satisfied with your model accuracy, you can quickly deploy another container in production environment and run live inferencing on your batch data. Now, in this case, for this demo's purpose, we trained the LSTM model, which is a recurrent neural network, and we trained this on a simple sine wave. The reason that we chose sine wave is just to stay consistent with what we have presented with Kinesis Analytics, and LSTM model is good at detecting any other pattern, not just the sine wave. And how we use this model is to first compute the next expected observation based on the past observation. And in this case, it will be the next data point on your sine wave. And if the next actual observation differs a lot from your predicted one, then we know that there's an anomaly, and that will generate a higher loss. And we can use this loss as an anomaly score. Now, to set the baseline, we take away 20 data points from a time series, and we just set them to 0. And we can see that the anomaly score computed is 153 times higher than a perfect sine wave. So. And then we introduce the bias on our sine wave, and we can see that the anomaly score presented is 93,000 times higher than a perfect sine wave. Finally, in the most challenging use case, as we presented before, we have a distorted kind of waveform. In the past, we were not able to detect this using random cut forest, but in this case, it is actually 20,000 times higher than the anomaly score computed on a perfect sine wave. So in conclusion, this shows that our model is working perfectly to detect the anomaly score on your data set. Now, since we have gone through why and how we implemented these 2 steps to detect the different kinds of anomaly, we have built a GitHub repository for you to deploy the entire cloud architecture on your AWS platform. And this can be deployed within 15 minutes. It's really easy to cause a CloudFormation stack, and that can do all the work for you. Now let's play the demo. Let's first clone this Git repo into our local machine and navigate into CloudFormation folder. Please note that in the environment file, there's a variable which you need to change to your AWS CLI profile name. Now let's deploy. The process will take around 5 minutes. We need to uncomment these lines to enable S3 notification and rerun this CloudFormation script again to avoid circular dependency in resource creation. This CloudFormation has created everything in our architecture except the Sagemaker stage. We can create the Sagemaker architecture manually by first launching a notebook instance and upload the prepared Sagemaker package provided in our Git repo. We can now navigate into Jupyter Notebook named Upload and Deploy and run the sections sequentially to launch the Sagemaker endpoint. The container takes around 10 minutes to deploy. You can check the deploy status by following CloudWatch logs. You will eventually see this in-service tag showing that it is done. Whenever new streaming data arrives in S3, the S3 notification system is going to trigger this Lambda function to run the new data through this Sagemaker endpoint and save inferencing result in the processed data bucket. Now let's go back to our local machine and launch our device simulator and generate some temperature sine wave data. We can navigate to Kinesis Analytics, observe both raw data stream and data stream with anomaly score computed. Please note anomaly score for the first few data entries should be 0 because random cut forest needs some initial data to begin computing. After around 5 minutes, you will see streaming data being delivered both as raw data as well as inferenced data from Sagemaker endpoint, and a graphical visualization of predicted value and real value. Finally, you can add customized anomaly into the simulation config to create all kinds of anomalies and observe how they generate different anomaly scores. Now, what to do next? If you're a business decision maker, let's identify IoT system risks and estimate failure indicators, like estimate what kind of anomaly pattern that equipment would produce, and collect failure data, and define reporting requirements, who to notify, whether it's site manager, your developers, and so on and so forth. And then get the best of both worlds by using simple algorithm to detect a simpler anomaly pattern that require immediate attention versus a fast time series inferencing pipeline powered by AI or ML to detect more complicated anomaly patterns. And now let's start implementing. And if you're a developer, we strongly encourage you to try this out yourself by deploying the demo that we just showed. Now, for additional resources, we provided a list for you to explore other anomaly detection strategies on AWS platform. Now, thanks a lot for watching. I'll see you next time.